Hi everybody, today we will discuss about computing components, that is from chapter 5. So we have the different layers image in this slide as well on the right corner. We already completed information layer and right now we are in the hardware layer. We discussed about transistors, gates, circuits. Now we will see some of the components that are in the computer. So the learning outcome of this chapter are, we will start with reading an advertisement for a computer. And we will see the components and functions in the von Neumann machine. Then we will describe the fetch, decode, execute cycle of von Neumann machine or computer. Describe how computer memory is organized and accessed. Name and describe different auxiliary storage devices. Define 3 alternative parallel computer configurations, and we will see the basics of embedded systems as well. So those are the learning outcomes of this chapter. So we'll start with a simple ad. This is actually an old advertisement. For the latest one, you can visit this website. I have included one of the computers advertisement from Dell that shows the latest specification. I mean, definitely the speed as well as the storage capacities will be different, but the basic features will be the same. So we will see how to read this Dell Inspiron 5000 model. So the properties or the configurations of the system are listed here. The first one is 2.5 gigahertz Intel Core i5. It's an Intel processor, Core i5. And the speed of the processor is 2.5 gigahertz. So hertz is a unit of frequency. The measurement is cycles per second. So basically in computer, there is a clock, a system clock that ensures that all actions are coordinated in the system. So the clock has got different clock pulses as well. For example, depending on what type of system it is, it can vary. So in this case, there is a clock which pulses 2.5 billion times per second. So that's what the speed of the computer is actually. So that 2.5 gigahertz speed, it's actually the speed of that clock. It matches or it synchronizes. Then we do have a FSB speed as well here. You can see just below the first line, it shows 1066 megahertz FSB 6 MB caching. FSB stands for front side bus. This is actually used by the processor to access data from outside, not from the cache, not from internally, from outside. So the speed at which the processor can get data from outside, that is from 1066 megahertz per second, which is lesser than the internal speed. So processor also has got a cache memory. The size is 6 MB. So basically, if the data is not there in the cache memory, it will take from outside. So if it is from the outside, it uses FSB with this particular speed, which is 1066 megahertz. Okay, the next one is the size of the screen. It's 15.6-inch full HD LED touch screen, 1920 into 1080. That's the resolution of the system. The screen. So basically, it's the width and height. Then we have 8 GB SDRAM, DDR3. SDRAM stands for synchronous dynamic RAM. So if it is 8 GB, we can have like 8 into 2 raised to 30 bytes of storage. Then we do have the graphics details, right? Graphics Intel HD graphics 520. That's the graphics card we do have. So it has got a memory as well. So the graphic processor, it will keep the data in its own memory. Then we have the hard disk details. 1 TB, that's the size of hard disk, 1 terabyte, then it's 5,400 RPM, revolutions per minute. So that basically shows how fast the disk actually can spin. So we know that nowadays this is actually replaced by SSD, right? Instead of HDD, we have SSD, which stands for solid state drive, in which data is written, transferred, and erased electronically and silently. Comparatively, it's faster, more durable than HDD or hard disk, more compact, quieter, and it consumes less energy as well. So those are some advantages. Then it has got a DVD read-write drive as well. On the right side, we have some wireless standards that are used in the system. So those standards like 802.11a, 802.11 BGN, Bluetooth, those are actually by the IEEE standard. IEEE stands for Institute of Electrical and Electronic Engineers. So that standard is what this computer system wireless devices supports. So that way we can ensure proper data communication. All right. Then it shows the camera, which is Intel RealSense 3D camera. Then there is a lithium-ion battery with 7-hour average life. It uses multiple ports as well. USB 3.0, USB 2.0, HDMI, LAN, audio, input, output ports are there in the system. Then we do have information about the size of the system, the laptop, which is 15 into 10.2 into 0.9 inch. That's the overall size. And it weighs 5.36 pounds. And it uses Windows operating system as well. I mean, in this case, it is Windows 10. All right, so if you go to this website, you can see more information about the latest computer. When you click on that, you will see different Dell laptop specification. I mean, sometimes you can see the latest operating system, latest processor speed, the Intel version, the Core i7. Some require only like very less power. Those information you can see over there. And the storage capacity will be different. Display capacity is different. The graphics card use will be different. Random access memory technology will be different. I mean, it's like LPDDR5. LP stands for low power, double data rate. Random access memories will be used. So when you get time, please go through that link. So here we have a table that actually shows the power, the storage, as well as the speed. If you look at the first column, you can see all are in 10 to the power. In the second one, it's in 2 to the power. So when we talk about the speed, the time, we usually use 10 to the power. And if you are referring to the storage capacity, we always use 2 to the power. So when you refer like 1 kV, based on whether it is referring the power or it is referring the storage, it can be different. Because 10 raised to 3 is equal to 1000. 2 raised to 10, when you take 2 raised to 10, it will be 1024. So that difference will be there. Yeah, so these are the different storage and speed that we can have in the system. So the storage capacity is actually increasing and the speed is also increasing. And the table also shows the prefix as well as abbreviation and derivation for each of those values. So a few things about the speed of a computer. The speed of a computer actually depends on speed of different components. So we do have CPU speed, motherboard, random access memory, hard disk, everything in this table. The CPU speed is actually measured by clock speed, and the unit is gigahertz. It's the time to complete one cycle. Motherboard speed, we always talk in terms of bus speed. how much data the bus can actually carry, not how much, like at what speed data can be transferred. And that is also taught in terms of megahertz per second, which is equal to the speed data can move on the motherboard from CPU to other components. That speed is what we measure in order to talk about the motherboard speed. Then we have random access memory. The speed is measured by data transfer rate, MB per second. That's the rate at which data to be transferred to or from the random access memory. Then random access memory also has got access time. That's the time for drive to locate the data to be accessed. So, I mean, if the data is in a particular position, how much time it takes to access that particular data. That is what access time meant by. And the transfer rate is a rate at which data can be transferred to and from the random access memory. Sorry, the access time is actually for the hard disk, okay? Because for random access memory, there is no moving part. So it won't take much time to locate the data. But that's not the case of hard disk. For hard disk, it will be spinning around always. There is a spindle and it will be rotating. So it needs to find out the data. That is what access time. It's for hard disk, not for random access memory. Okay. Access time is the time for drive to locate the data. Then data transfer rate, that's the rate at which data to be transferred to or from the hard disk. Next is about the major parts of the computer system. We do have motherboard, CPU, graphic processing unit, GPU, random access memory, and storage devices as well. So I have included the link for a YouTube video that shows the major parts of the computer system. So I strongly recommend you to watch that video so that you will get an idea about how those devices, not devices, the components actually looks like and how it is connected, how it is integrated together on the motherboard. So please watch that video when you get time. So next is about stored program concept. So basically this figure shows the architecture of a von Neumann computer, von Neumann machine. These are the basic components that we have in the system or in the architecture of the computer. If you look at this, you can see on the left side, we have some input devices. On the right side, we have output devices. Input devices will accept the data, right? User can give data to the system using input device. And through output device is what we are getting the data, or we watch the video, we watch the output, the document on the screen or the monitor. Those are the output devices. And in the middle, we have two units, mainly central processing unit as well as memory unit. Central processing is where all the processing has happened, right? The CPU mainly divided into control unit as well as arithmetic and logic unit. And the data from memory will be taken to the CPU for processing. And after processing, it will be given back to the memory as well. So this is the basic architecture. It's called von Neumann architecture of a computer. So the instructions and data are both stored in the memory unit. So remember, like if you want to store any data in the system, it needs to be in the binary format, right? So it goes to the memory. The data will be in the binary format. And we need to give instructions to the computer. Then computer will work based on that instruction. That instruction also will be in the form of binary. So it's not easy to distinguish whether it is a data or whether it is an instruction, because both are in the same format. So here we have the memory representation. On the right side, we have the address as well as the content. So the memory is actually divided into smaller cells. Every cell has got an address. If you look at this one, you can see it starts from 0000. 8 bits are there, and the last size will be all 8 bits will be 1. So that's the capacity of this particular memory unit example. And in each cell, we can see contents as well. So every memory location has got address. And if we have some data or if we have some instruction, those instructions can be stored in those memory as well. That is also in the form of bits or binary values. So a collection of cells, each with a unique physical address is what? Memory. Most computers are byte addressable. You can see, if you look at the table, you can see each and every address and the contents, it consists of 8 bits, right? Then there are like, I mean, we actually call this as byte addressable memory unit. And this is the little endian bit numbering representation as well. So you can see the contents in the small table at the bottom. The position actually starts from 0 till 7. So altogether we have 8 locations, right? And in each location, we have the data as well. In 0th position, we have 0. 1 position, we have 1. Second, 2's position, we have 0. So that means every bit position consists of values as well. Then, sometime when you see the binary values, any binary value, it's not easy for us to distinguish that, like whether it is an instruction or a number or an integer or part of an image. It can be anything, right? Because everything in the computer is stored as binary. So if you see, I mean, when you see a particular number, for us, it's not easy to distinguish that or identify that, whether it is an instruction or it is a data. It can be anything in the memory. Next is arithmetic and logic unit. ALU actually operates on words, 16-bit, 32-bit, or 64-bit. So basically, those are the number of bits processed by arithmetic and logic unit. ALU is the one that performs basic arithmetic operations such as addition and subtraction in the computer. Also, it performs logical operations such as AND or NOT. So most of the operations are like logical operations. So those basic operations will be performed by ALU. Most modern ALU have a small amount of special registers. I mean, it's kind of storage unit. We can call it as registers that can be accessed faster than main memory. So inside the ALU, there are like very small storage unit that also we can use to store data, instructions. So different registers are there, general purpose registers and special purpose registers. We will see some examples in the coming slide. So input unit and output unit. Input unit is something that we can use to give inputs to the system or data or programs to the system. Different inputs units are there, like keyboard, mouse, those are examples. Then output units are devices through which results stored in the computer memory are made available outside the computer system, like printer, the scanner, then the monitor, speaker. Those are examples for output unit. Then these are some of the examples of registers that we have in the ALU. So the CPU is divided into control unit as well as ALU, right? The control unit is like the organizing force in the computer. That's the one controls every action performed by the computer, performed by the CPU. And the registers in ALU, we can use those registers in order to store different data or different instructions. I mean, it's like a very small storage location. Few examples are listed here. One is instruction register, that stands IR, instruction register. It contains the instruction that is being executed. So CPU will be executing some instruction always, right? So those instruction details will be there in the instruction register. I mean, the instruction that is currently being executed. Then there is another register called program counter, PC. Program counter contains the address of the next instruction to be executed. So always PC will be ready with the address of the next instruction. That means address means, see, initially those instruction data, everything will be there in the random access memory, right? From the random access memory, whenever it needs to be executed or whenever CPU is ready, CPU will take those instructions, right? So PC actually contains the address of the next instruction. That means the address of the random access memory from where we can get the instruction. That means it will be ready so that once the current instruction is executed, once it is finished, program counter will give the address of next instruction so that there will be instruction executing always. So without any delay, processing will happen. Okay, so ALU and the control unit called the central processing unit or CPU, together ALU and control unit. Next is the flow of information. So here we have like certain components which we have in the von Neumann machine, like input devices, CPU, main memory, output devices. So all are actually taking data from the bus. Bus is like a communication system that transfer data between components inside a computer or between the computer. You can see all the devices in this figure, those are connected to the bus. Input device will give data to the bus. CPU will take data from the bus and also it passes data to the bus, likewise main memory. Output device get data, or I mean whatever data needs to be displayed, that is also taken through the bus, I mean from the bus. Maybe it's coming from the main memory. So through bus only it goes to the different devices. So in simple words, bus is a communication system that transfers data between components inside a computer. The same way, the bus that we use for public transport, that communicates or helps in commute, right? We can move from one location to another location. The same way, in computer, bus is also used for exchanging data or for communication purpose. So when you see like n-bit processor, when you see that term, it can be anything. The general registers might be using n bits to store the data. The ALU might be processing n bit of information. Sometimes it will be about the address, how many bits are used to store the data. Sometimes it will be the bus size, how many bits the bus can transfer or process. So it can be any of this when you see like n-bit processor. Next is the fetch execute cycle. It's all about how CPU actually takes instruction from the computer, from the memory, and how it takes data from the memory and how it executes. So that is actually a cycle. It happens like a cycle. The different steps involved are, first instruction needs to be fetched. Then that instruction needs to be decoded. Then if there is any data needed, that needs to be obtained. Finally, the instruction is ready, data is ready, it will execute. So it happens over a cycle. That's why it is called fetch execution cycle. So this is the format of that. So we know that the program counter, that will be ready with the address of the next instruction. So whenever the program counter has got the address of next instruction, CPU can actually get that address and it can get the data, or I mean the instruction from the memory, right? So what the control unit does is, control unit will go to that address in memory, because PC consists of address of next instruction. So control unit will get that address from the PC, then it goes to the memory, and from memory it will take that particular instruction. And what it does is it will take the instruction, and a copy of that instruction will be stored into instruction register. That means currently this instruction is what CPU is going to execute. Instruction register consists of the instruction that is being executed, right? So that instruction is loaded into what is called the instruction register. Okay, then it has to decode the instruction. So the instruction can be any type. Maybe it's to access data from a keyboard or any input devices. Sometimes we have to send some data to the output devices. Sometimes it will be kind of operation like addition, subtraction, any type of operation. So it can be anything, right? The instruction. So that needs to be decoded. Instruction will fetch first, then instruction needs to be decoded. So at this phase, what happens is the control unit will decode the instruction into control signals. That is, the logic of the circuitry in the CPU determines which operation is to be executed. So that's the way computer actually executes multiple instructions. Okay, then now we have the instruction. In case if there is some data needs to be taken or obtained in order to complete the instruction. Say, for example, if it is an addition, we need the data, right? So that is the third phase. So after decoding the instruction, it will get the necessary data to the registers in the ALU. Then finally, the instruction will be executed. So once the instruction is ready, once the data is ready, instruction will be executing. That's the last step, which involves sending signals to ALU to carry out the processing, whatever the processing. So that's the fetch execute cycle. Next, we will see random access memory. Random access memory is the memory in which each location can be accessed and changed. Read-only memory is a memory in which each location can be accessed but not changed. RAM is volatile in nature, ROM is not. Volatile means when you turn the system off, when the power goes off, there is no data in random access memory. Everything will be wiped out from the random access memory. So we know that during booting, many process will happen, right? When you start the system initially, when you give power to the system, the booting process happens. So programs like operating system will be loaded initially. Then rest of the programs that are necessary for the system to work also will be loaded. Then, I mean, loaded in the sense, those things are permanently installed or stored in the hard disk. Say, for example, if you have hard disk, right? Then while execution or during the booting process, those things will be loaded to the random access memory. Then later on, as we require more data or any program needs to be opened, it also will be brought to the random access memory. That's the way it works. Then when you turn off the system, those data from RAM will be erased, but it will be there in the permanent storage area. And we need some secondary storage devices as well, right? So ROM, there are like erasable, programmable, read-only memory as well. And we use different secondary storage devices in order to store data. That's like a permanent storage where the data is non-volatile. I mean, the device is non-volatile. Even though there is no power, the system will store the data. System will not wipe out the data. Yeah, so we will see some examples for such devices. One is magnetic tape. This is kind of old device that we use. This is the first truly mass auxiliary storage device that is used once upon a time. We do have a sample figure, I mean, image of magnetic tape over here. So it uses like tapes. You can see those tape reels over that cylindrical shaped icon. Then if you want to read a data, you need to get it from the tape. So what it happens is when you move the tape, I mean, the tape will go near to the read-write head. When it reaches on the read-write head will read the data. And the tape motion will be in one direction, you can see. And it actually goes to the other cylinder where we have the take-up reel. So the problem with this kind of storage is, if you want to read a data that is somewhere inside that particular reel, you need to access all the data. I mean, random access is not possible. You have to access one by one or sequentially. You cannot just jump into a particular position and you cannot access data from that. That is one of the disadvantage. But in early days, this is the way we store data, or this is a device that we use to store data. Then we had like magnetic disk. Magnetic disk, I mean, on the left side of this slide, we have a single disk representation, how the data is organized, or how that disk is divided into different parts so that we can store the data. A single disk representation is what we have on the figure A. And on figure B, we have the picture of a hard disk drive. So in the drive, we can see multiple disks are actually organized together. It's like a stack of plates. So here, if you look at the single disk, you can see different tracks over there, multiple tracks. So, I mean, those are the concentric circles that we have on the surface of the disk. So there exist multiple tracks. And you can see each track is divided into sectors as well. And each sector holds a block of information. Those are contiguous sequence of bits. And each track also has same number of sectors. In certain cases, it can vary as well. So that's the way one magnetic disk look like. The same way we will have multiple disks attached on the system. And on the disk, on both sides, we do have the data. So we have magnetic, read-write head, which can actually read data from top as well as bottom. That's what's shown on the right side of the slide, the image on the right side. So that is the disk drive. So we have an arm at the right side. Then from there, we can see the read-write head. Then there is a spindle in the middle, around which we can have the cylinders, I mean the platers. So data will be recorded on both sides. Then this will be moving always. So whenever you want to access data, this disk will be moving, and the hard disk read-write head, that also will be moving this way so that it can access data properly. So read-write head always moves from one track to another track. So if it is on the right track, it waits for the correct sector to reach beneath the head. That way it will read the correct data. So both, I mean, it will have a rotation as well as read-write head will be moving. Okay, and those several platters will be attached to the spindle, and the spindle will be rotating. Each platter actually has got its own read-write head, as in this figure. And there is something called cylinder. You can say cylinder. Cylinder means it's, it's from all the tracks that line up under one another. So the same track that line up under one another, that is what cylinder meant by. So when you try to access data, it actually has got an address as well for that location. It shows in which cylinder it is, and the surface number as well as the sector number. So the disk actually need all those information so that the read-write head can read the data or write the data into that particular location. So we do have like few terminologies related to magnetic disk. One is seek time. Seek time is the time for read-write head to be over a right track. So it will be rotating, right? And there exists multiple tracks on a surface. So read-write head will take a little bit time in order to position to the right track. That is what seek time meant by. Latency is the time for sector to be in position. So the disk is rotating. That rotation will make the particular sector to be in position. That time is what latency meant by. Access time, it is actually the sum of seek time plus latency. By that time, we can access the data, right? Then we have transfer rate also. That's the rate at which data moves from disk to memory. Memory in the sense random access memory. So from the disk, we might need to get the data into random access memory so that CPU can execute, right? So that's the way it is connected. Then we have optical disk, CD. It's a compact disk that uses laser to read information stored optically on a plastic coated disk. Data is evenly distributed around spiral track. CD-ROM are there, which is read-only memory. CD-DA is there, which we use in order to store digital audio. Then CD-WORM is there. WORM stands for write once, read many. RW or RAM CDs are also there, both read from and return to the CDs. Then DVD is another example for optical disk. It stands for digital versatile disk that is also used for storing audio and video. Compared to CD, more data we can store in DVD. Blu-ray is another example. It's a high capacity DVD allowing higher resolution video. So those are some examples. Next is embedded system. Embedded system are computers. I mean, in a way, those are like computers that are dedicated to perform a narrow range of functions as part of a larger system. So typically, an embedded system is housed on a very small or simple microprocessor chip with the programs stored in read-only memory. I mean, if you look around the devices or the appliances has got embedded system. I mean, those are examples for embedded system, which consists of a small microprocessor chip. Say, for example, the digital devices that we use, like watches, microwave, car, the dishwasher, dryer, I mean, washing machine, all those devices has got embedded system in that. So it uses small computing power in order to perform a narrow range of functions. So it has got a specific function, right? Fridge does something, microwave does something else, the dishwasher does something else. So it performs a particular function, but in order to execute that, it uses the computing power as well. I mean, the smart devices that we have nowadays. Next is parallel computing. Parallel computing is all about breaking down a larger problem into smaller, independent, similar parts that can be executed simultaneously. So a big problem we can divide into smaller ones. And those can be given or executed by multiple processors. And those processors needs to be communicated, right? There should be communication between that. And those will be used in kind of shared memory as well. Finally, the results from different computers will be combined together. So a big task can be performed with the help of multiple systems. So in different levels, we can execute this parallelism. One is bit level parallelism, in which multiple bits are processed. Instruction level parallelism, multiple instructions are processed at the same time. So you can give multiple instructions to different CPU. Then data level parallelism. So one particular operation can be performed on different sets of data. Then in task level, multiple tasks are given to the system in order to process. So at the same time, multiple tasks will be executed by different systems. So that way we can improve or enhance the computing power of the system. And such parallel computing uses shared memory concept as well. You can see here we do have like multiple processor in this figure. So each processor has got its own local memory. Processor 1 has local memory 1, processor 2 local memory 2, like that. It has got its own local memory. At the same time, it uses a shared memory as well. So say for example, a part of one task will be executed by processor 1, and that output may be used by a different computer or a processor, not computer, processor. So it will put that data into the shared memory. The other computer can take from there. So that way, the systems will share the memory. That way, the speed or the capacity, the processing speed and efficiency can be improved. So a larger problem will be divided into smaller ones, and each processor will be taking care of those smaller operations. Finally, we can combine the results from all the processors together, and we will be able to solve a bigger problem. That's the concept behind parallel processor. So this is the works cited. That's all from this chapter. So this is all about the components in the computer system, the hardware components. So we talked about the von Neumann architecture and different parts of the computer system, memory, different storage devices. Okay, that's all from this chapter. Thank you.